Hello, my name is Reese Clendenning. Today I'm going to be walking through a procedure for the spectrophotometric determination of iron in a river water sample. Now, first of all, why do we care about the concentration of metal ions in water samples? Well, metal ions are going to play important roles in all sorts of geological and biological processes. Some of these are necessary for life. However, most, if not all, metal ions will become toxic if they are present in too high of concentrations. So for instance, for iron, the EPA's criterion for continuous concentration is 1 ppm, so 1 part per million. That's the highest recommended concentration that will not result in long-term damage to aquatic life. Iron can also signal a host of other problems, so high iron concentrations commonly accompany things called acid mine drainage, and if left untreated, that will make the water eventually become inhospitable to life. So that's why we care about this, and we're going to run through a procedure for hopefully accurately determining the concentration of iron in a river water sample, in our case, the Wabash River. So of course, we have several materials. We need a river water sample. It's best if this is collected as close to the experiment as possible, and also in an area with low turbulence. So you don't want a whole bunch of precipitant, you don't want a whole bunch of solids in your water sample. And it should be stored ideally in a dark brown container, also refrigerated if you have to store it for a few days. Then we have our chemicals that we will need. We're going to need sodium acetate, that's going to be our buffer. Hydroxylamine hydrochloride, this will act as a reducing agent. So iron in water samples is commonly iron 3 and iron 2. We want to convert everything to an iron 2 plus or ferrous state. So that's what the hydroxylamine is for. We will need 110 phenanthroline. I've already prepared a solution of that. That's 5 millimolar. That is going to be our complexing agent that will complex the iron to ions in solution and result in a colored species which we can measure on the UV vis. We will need then an iron standard solution. So this is made of ferrous ammonium sulfate, and I have created a 1 liter solution that is about 10 ppm, so 10 parts per million. The last thing we will need is sulfuric acid. That will be used in the preparation of both of these solutions, as well as in the treatment of our water sample to help digest any iron hydroxides and prevent basic conditions which tend to precipitate iron. We want to keep all of the iron in solution. We have our instrument, right? So today we're going to be using a SpectroVis Plus. This is going to be communicating with our laptop here, and we'll be able to record UV vis data using that instrument, but of course any other UV vis will work as well. We need then our volumetric glassware. So ideally, you will be using volumetric flasks. I've got an assortment of 100 milliliter volumetric flasks here for making our standard solutions, and then for preparing our diluted sample solution. You'll need graduated cylinders, there we go, for measuring various volumes of solution. These do not have to be super precise, but we will use the graduated cylinders to get a rough idea of what those concentrations are. We need an assortment of beakers for things like filtration of our sample, waste collection, making up our solutions, and then along with that, we'll need a funnel and then some sort of filter paper. We'll use that to remove any sediments that do come from our sample, which will hopefully be minimal. And that step is not strictly necessary, but it will make data collection a little bit easier for us in the long run. The last major piece of equipment is going to be our volumetric pipettes. Now there are a couple of different kinds of volumetric pipettes. Here I have kind of your standard single measurement volumetric pipette. This is going to deliver, this one in particular delivers exactly 25 milliliters. We'll also be using, just to demonstrate both, a serialized volumetric pipette. Now these are slightly less accurate. It's easier to have user error in these. However, the advantage of this is that I can deliver any volume quite accurately from 1 milliliter to 10 milliliters. So we're going to be using these then to deliver exact amounts of standard into our volumetric flasks, and that'll allow us to create a set of standards of various concentrations that we know. So that's the basic overview, and now we can get started making up our solutions.